I should just explain a little bit the strategy that we've been pursuing. So we've started off describing stuff in the laboratory, and then we have this, we sort of extend linearly that so we can get this equivalence framework that allows us to think about taking the sort of linear sum of things in the laboratory. So I explained that, and it invokes this P function. And now what I'm working on is this correspondence into something else, which I call the operator tensor framework. And that's the thing I'm going to talk about today. Let me make this full screen. Okay. But to get that correspondence, we need to invoke these duotensors, okay, with the black and the white dots. So that's kind of been the objective. And we've discussed duotensors in the case where they come from this operational equivalence framework. And then I want to discuss duotensors also in this operator tensor framework. So maybe I should just go back a little bit and show you how those work and see if that. Oh, I've actually gone too far back. I start again there. No, I was starting at the wrong slide. So okay, let's go. Okay, so we have this principle of decomposition locality, which is using these fiducial elements. You define fiducials for the pointers, and you use this idea of that you can linearly expand operators in terms, so operations in terms of operations, and that's what the fiducial elements allow. They allow you to expand arbitrary preparations like this one in terms of a special set, the fiducial set of preparations. And the same thing for results, and the same thing also for system preparations and system results. So in each case, the fiducial element has a black dot on it, and then the expansion matrix has a white dot. Okay. And this is using these notions of equivalence invoked using the P function.
So this fiducial element for the equation 49, the left one, can I think of as like kind of a preparation of a basis state?
So this would be, so at this point I'm talking about it in the laboratory, but in quantum theory what it corresponds to would be a spanning set of positive operators.
Sorry, the left one is the spanning set of.
Excuse me. Okay, this one here, this would be a spanning set of preparations.
Right. For example, they are the preparations for in qubit theory. I could think of the preparations for plus X state, plus Z state, and plus Y.
Yeah. So a good spanning set would be exactly that. There should be some normalization because these things in the time symmetric theory aren't necessarily normalized. So there's something here, I'll just call it K. And then so this, and then you could also have, these are qubit states. They say there's a Z. Then you could also have
X
plus for X and plus for Y.
Okay.
So this set of four states, four projectors for positive operators span the space of preparations in quantum theory.
Right. And then in equation 50, left-hand side, the A white dot.
Yeah.
This one, how do I think of?
Well, imagine I want to write down an arbitrary row in standard quantum theory. I can write it as some sum of each of these projectors with some various coefficients. A1 plus
right. So it's kind of the fiducial elements. They are the operator basis, and the A y dot are the coefficients.
Yeah. Except, actually, what I've shown you are these things these are not actually operators. They're things in a laboratory. Because these are basically prescriptions on how to do various preparations in the laboratory, but they correspond in quantum theory to these positive operators.
Right. Here you emphasize that there are things in the laboratories because we haven't taken the equivalence.
Yeah, but we haven't set up the correspondence. Yeah, and I'll show you that correspondence shortly. Yeah. Anytime. Okay. So that's the idea. We're just going over the stuff from the end of the last lecture because I went through that a bit too quickly. And now in this sort of language, under that correspondence, which I'm going to come to, you know that you can write down an arbitrary operation as a weighted sum of the tensor product of the spanning sets associated with each of the inputs and outputs. This is a thing that's true in quantum theory.
And then the fact that this decomposition locality is equivalent to tomographic locality is because only with tomographic locality we can write out an arbitrary operation in terms of the coefficient of this operator.
Yeah, I mean,
product operator basis.
Yeah, that's right. Yeah, I mean, there are some proofs in the book explaining all this, but you can show. I mean, this thing is almost obviously equivalent because if I just cover everything up, if I cover all the inputs up, then you've kind of got you can see that you can write down an arbitrary preparation in terms of a sum over. So it looks like from this, it's almost obvious that you've got tomographic locality. It's kind of the dual statement to tomographic locality. But you can prove, and these things are in the book, that this is equivalent to tomographic locality.
So in the case where tomographic locality fails, we cannot have this. We cannot write an arbitrary operation just as a matrix, like a tensor in terms of this.
Yeah, right. Yeah. So it's easy to go that proving it in the other direction, showing that tomographic locality implies this is a little less obvious, but you can do it.
Okay.
And Balji gave a lecture. When was that? Like a few months ago, in December, talking about the similar things, really. Okay. Yeah, and so these expansive matrices are white. And then I went through defining these fiducial matrices, which are basically the probabilities of the fiducial circuits. In each case, you can write them as being equivalent to the fiducial circuits because circuits are equivalent to their own probabilities. And remember, the notation is a bit weird here. Really, there should be an x and an x prime on each of these black boxes because they are independent variables because you have a matrix. But just when you have these diagrams, it's more convenient just to put x's there, so you know the typing. Okay.
So we should read it as two of the same x.
We should read it as being there's x here and x prime here, so you've got a matrix. So this x, you should think of this as x and x prime. So this is like basically a square matrix. I'll show you an example of the square matrix in just a moment. Okay. Maybe I can go ahead and show it to you now. There. Okay. So this is the square matrix for the pointers. And this is sort of just a choice where you your fiducials correspond to these things, your fiducial preparations correspond to this, your fiducial results correspond to this, and so if you sandwich those together, you just get this. You have x, you have an x here and an x prime, you only get ones down the diagonal, and you get zeros everywhere else
Is
because of idempotency, whatever it's called. Yeah.
seeing that circuit with the two black dots and X.
Which one? Go back. You want me to go back?
Just, yeah, the ones that we're talking about.
Yeah.
The thing on the left-hand side of that equation. It looks like a closed circuit, so I would expect it to be a scalar, which seems to be.
Which one? This one? Yeah.
Well, just the thing on the left, that.
This. Yeah. So this is actually just a mathematical object. It is just numbers.
But is it the scalar or is it the matrix?
Oh, right. It's a matrix because you've got these two open wires here which have these labels x and x prime. But the entries are all equal to probabilities of circuits.
Okay, so you kind of read it as if x was a free variable.
Yeah, maybe that's the way to do it. Yeah. So you have to do, in the case of a qubit, you could do this. You could determine this by this is classical. These are pointers. So you would just send in you would have the different preparations and yeah. Okay. Then you have the white dots is the inverse. Okay. There's various rules for manipulating these black and white dots, which I don't think I should go through again, but the key thing is that you can change the order. If you have a black white dot followed by a white dot, you can make that a white dot followed by a black dot. So you can just represent that by the straight line, because it doesn't matter which order you put those black and white dots in.
Should I think of this as a resolution of the identity equation? Like, are we implicitly summing over something?
Yeah, everywhere a black and white dot meet, you're summing over that. Yeah, so, I think I showed you in this thing here. Every place there's a black and white dot, you're summing over the variable that lives on there. Yeah.
So can I ask something about what you said in the very beginning? Like, if I look at equation 51, some of those things that have a black dot, and then some circuit out of it, you said we should think of them as laboratory procedures. Am I right?
Yeah, they correspond to things in the laboratory. These are fiducial elements. So, those are things that an experimentalist can put in place.
Okay, but not as equivalence classes of them, just as like.
You could, so this could be a preparation. This thing here of a qubit. Say if small c here is equal to 1, that could correspond, if this was a qubit, to preparing a qubit in a spin-up state. I'm speaking too fast. Really, what you can do is you can do an indeterministic preparation, where if the light flashes, what you've done is prepare a spin-up state. Because it's the time symmetric theory. So these things are not normalized necessarily.
Okay, but can I think of it also as the actual vector that represents the speed?
So that's the next part of the lecture is where you have this correspondence to those vectors. Yeah. So you've got the things in the laboratory. And then you have the mathematical objects they correspond to. And I like to separate those out because they're different things.
Yeah. And the dual tensor calculation, because like the C thing with the white dots.
Mm-hmm. The big C, yeah.
This is a matrix or a number.
This is really it's I call it a duotensor, but it's really a hypermatrix because it's got a lot of. But it is, yeah, it's essentially
okay, like a linear map.
Yeah, it's a big set of a big bag of numbers. Yeah.
Okay. So like the dual tensor calculation is essentially what's translating the laboratory stuff
into the. That's what's going to happen. Yeah, and so I've only told half of that story.
Okay.
So yeah, so if you take this thing and then let me just now go forward and look at the how that story works. Okay, so you start off with an experiment. Okay, this is fully in the laboratory.
Yeah.
But you can replace each of these boxes. There's many boxes in this. There's the A box, there's the X box, there's the R box, so on, all these different boxes, you replace them by their decomposition local form. Okay, so focus on the B box. If you look at this B box, I can trace out the thing I've replaced it with, which is so you've got this duotensor with white dots on it, and then you've got a fiducial element leading off that in each position. And I've done that for every single box. And I did that using ticks. Yeah. So that's the first step. Is that clear? Yeah. And then what you do is you look and see you get all these fiducial circuits. Okay, coming in. One thing I should mention is, so what you've got at the moment is a hybrid object. It's all the duotensors with the white dots. Those are bags of numbers, but these fiducial circuits are things that you would have in a laboratory. And remember, in the, I think it was the first lecture, I showed how the probabilities over circuits factorize. Okay, that's really playing an important role here because you have lots of different circuits in parallel, and then you have a sum over all those circuits. So it's important the probabilities for all these circuits, these fiducial circuits, factorizes.
Mm-hmm. So should I read the thick wires? There's some wires, short wires, which are a bit thicker, like inside the fiducial.
Yeah.
Those are like the, I don't know, abstract
System.
operational objects in.
Yeah. So I've adopted this notation where I use thick wires for pointers, because for me pointers are more substantial. Those are the things you actually can look at, and I use thin wires everywhere else. So here's also this is a system as well, passing between. This is a real system.
Yeah, that looks like it's equal in width to the lines that you've drawn.
Yeah.
To those ones. Yeah.
Yeah.
Is that significant?
The
same.
I would say the way to reduce significance is the wider part of this trapezoid shaped object is where the physical system comes out or goes into, and then the narrower part is where the mathematical label tags onto it. Yeah. Okay.
When you say these boxes A, B, and C, they are now bags of numbers.
Yeah.
Does it mean that these wires that come out of them should be interpreted as classical random variables?
I mean, if you in standard quantum theory, if you took an expansion, if you took a density matrix and expanded it in terms of some positive operators, okay, then the expansion coefficients would have some labels on them, say superscripts. The indices, yeah. And so the numbers that live on these wires are those indices. They're the expansion indices. Okay.
Yeah, so I could interpret the wires themselves as vector spaces.
You could, yeah. You could say they're real vector spaces in some sense. That, and these things, these objects here are tensor-like. Okay.
By the way, another question: why? So, what makes these into duotensors?
To duotensors, because they have black and white dots, and so there's some extra stuff going on where you can change the black dots to white dots. A similar thing happens in general relativity. If you're familiar with the Vielbein representation, the Vielbein, or it's sometimes called the tetrad formulation of general relativity. And there you get tensors, and they don't use black and white dots, but there are two kinds of labels that live on those tensors and a way of turning one kind of label into the other. Okay, so this is not a new kind of structure. Yeah.
And then when you say here, you have a lot of circuits that factorizes. So in this picture, a circuit is something that is surrounded by black dots.
Yeah, that's right. That in this case, that marks where the circuits are. But the main thing is, look, these things are things in the laboratory. Yeah. So. Right.
So here we have a combination of a bunch of circuits that is surrounded by black dots and these duotensors, which are the coefficients.
Yeah, exactly. Yeah. So that's what's happening. So we've gone from this situation, which is an experimental laboratory, to an equivalent situation where you've got a product of many circuits, many fiducial circuits, with coefficients in front of them. Yeah, so that's mathematically what's happening. And this has still got physics in it. So the next thing we do is replace each of these fiducial circuits by the fiducial matrix, okay, which is equivalent. It gives us that. But now each of these is now just numbers. So this thing now is entirely mathematical. There's no physics left in here.
And the fiducial matrices depend on your choice for your fiducial.
Exactly, yeah.
It's not always this diagonal.
No, they could be, yeah. And in quantum theory, the fiducial matrices will have, will definitely have off-diagonal terms. And the inverse of those fiducial matrices, which we don't have here, will have.
This is because, for example, if I choose the fiducial elements as, say, these plus, these ones, and then between plus z and plus x, I would have a...
Exactly, yeah. Good, exactly, yeah. Yeah, and then when you take the inverse of that object, you'll get negative numbers, typically. Okay, and now we've got this big thing, but we can just, because it doesn't matter which order these black and white dots appear in, we can just replace all these black and white dot pairs by just straight lines, okay? And if you want to evaluate this, you reinsert black and white dots however you want, it doesn't matter.
And now these little boxes, they are still readout boxes, but the wires, they are no longer the pointer system, the wires become.
Yeah, and there is actually, these little boxes are the duotensors representing readout boxes, because look, they have different font on the wires. So we started off with this thing with the \math_TT font. So these are the readout boxes which correspond to stuff in the laboratory, and then we replace them by these things which just have normal math font on the wires.
So this normal math font, they are the indices.
Yeah, they're the indices. Yeah, and so this whole thing is mathematical. There's no physics left in here.
The indices of the fiducial measurements.
Yes.
They look the same as the label that is in the readout.
Right. Yeah, and that's a potential source of confusion, which I think I talked about earlier. Oh yeah. Well. Yeah. Here. So here's. So yeah, it's right. That's potentially confusing. So the way to interpret this symbol is that x inside there is a specific value of x. Okay. Whereas the x's on wires tell you what kind of wire you have. Okay. And yeah, I admit that that's a source of confusion. However, once you understand that, it's much easier to proceed with this notation than use primes and whatnot everywhere.
They do range over the same set of possible.
They do, yeah. Because that's how many you have, so that's how big the vector space is in the case of the.
This is like it's essential that we're talking about horizontal wires here rather than the.
With the vertical wires, yeah.
Might be d squared.
That's right, yeah. And I don't have readout boxes on the vertical wires, yeah, because they're on the other side of the Heisenberg cut. Yeah. Okay, right. So the main thing is we got to this. Okay. And now we want to tell the same kind of story, but yeah, go ahead.
Can we just go back one step? Yeah, here. So here we have this, for example, if we look at the B line.
This one here?
Sorry, the horizontal, the one. Yeah, we have this Y.
Sorry. Yeah.
The Y on the fiducial matrices, not the readout box Y, the one on the fiducial matrices, they are the ones.
Which one? These ones?
Yeah, this one. I think I'm still a bit confused about the relationship between this Y and the Y in the box.
So what I could have done to make this simple is I could have put actual numbers in here. I could have put like this could be a 7.
Okay.
And this could be a 3. This could be a whatever 27. Depends how many outcomes you have. Okay, but still on the horizontal wires, I want to sum over these things. So here, I'm summing everywhere there's a black and white dot meeting or a straight line. I'm summing over the corresponding label. So is that clear? You don't seem fully convinced. So let's imagine that y takes values from 1 to 30.
Okay.
So here I sum from 1 to 30. Here I sum from 1 to 30, because this is a matrix, this is a coefficients. Here I have a particular value of y, say 27.
Okay.
Here I sum from 1 to 30, and here I sum from 1 to 30.
Okay.
Yeah. So that's the, yeah, that's the point. Okay. Oops. So we get to that. Okay.
So can I just look at does anything change on the inputs and outputs fonts, or are they the same as the beginning, the first?
Which one, say? Go back more?
The circuit we start with and the circuit we end up with?
Okay, yeah, it does change as well. So so I used on those, because here we want to label, in quantum theory, this label would run over from 1 to n squared, where n is the dimension of your Hubble space. So I use this funny font. Sorry, I can't remember what it's called. It's like \math pz something. Yeah, you can only use so many fonts in LaTeX before they start getting up, before it gets upset. And I've used pretty much as many fonts as I'm allowed. Because so I use that font to represent running over that label, which is, which.
Okay. And then in the last one,
it's the same label,
okay.
Yeah.
Cool.
So here the idea is that in a theory satisfies tomographic locality.
Mm-hmm.
You can just turn the circuit describing laboratory procedures into the matrix representation.
Yeah, and it looks the same. Yeah, but it's now just replaced with duotensors. Yeah.
Okay, thanks.
So that's the key thing. Yeah. And when you evaluate this circuit, you don't have to foliate it in time as you evaluate it. You can choose to sum of these in any order you want. So you're not forced to think of the system evolving in time. Like people normally think about a quantum system evolving in time through a circuit, and then the mathematical calculation corresponds to that. But that's not necessary. Okay. So I'm trying to form this bridge between the equivalence framework and this, and everything I just did was based on the operations, because I had the fiducial operations. So now I want to do something similar over here with operator tensors, and then sort of connect that bridge. So I want to connect to this diagram using operator tensors, and then I can form the correspondence. Okay, so this is the idea. I start off, I have operations, which are things in the laboratory. I want to form a correspondence with these things, which are called duotensors, and I'm using the same symbol in bold in this case if it's deterministic, or not bold if it's not deterministic, a hat, and then a double border box. Okay. I'm going to drop that hat if there's no system wires, because it doesn't seem right to put a hat on some object which is just classical. And this thing is I call it an operator tensor. In quantum theory, it's an element of, well, if you go around and look at the wires, for the classical wires, we just have an n-dimensional vector space. And for the system wires, we'll have Hermitian spaces. Okay, I'll talk about that a bit more later. And we want this correspondence between these to be such that for any circuit, the circuit in the laboratory is equivalent to the operator tensor calculation. Okay. Notice how the R doesn't have a hat on it because it's only got a pointer. Okay. Okay. So that's the objective.
So I'm not sure if I understand. So the left side of this diagram is purely sort of in an operational theory, not assuming any quantum
Yeah.
stuff, right? And on the right-hand side, it's the quantum.
Yeah. So we're going to have to make some assumptions to make this work, and I'll show you what those assumptions are.
Okay, so like operational assumptions that effectively end up boiling down to assuming quantum theory.
Yeah. We want to put quantum theory in that operational framework. Yeah.
Is that the same as you did before when you calculated the operation, the dual-tensor representation of a circuit, and then you showed that it looked the same?
Yeah, except now look, there's a double border boxes and there's hats. So these objects are operator tensors, not duotensors.
So the difference is here you're kind of doing the reconstruction program, like your 5 axiom stuff.
Yeah, I mean this. This is not so much about the 5 axioms or reconstruction. This is about, because we're used to using operators to represent objects in quantum theory, operators that live in a kind of Hilbert space or emission space. We're not used to using duotensors. Okay, so I want to get us into familiar territory, and I haven't done that yet. So this is about doing that bridge. But basically, the duotensor is going to live below this, help this translation. So I'll show how that works.
See, so the dual tensor, they are the coefficients in the boxes, but now the thing in the boxes, they are the not the coefficients, they are the operator tensor.
Yeah. I mean, they share in common that they're both mathematical objects, and it's going to be just equivalent ways of representing the same information, as you'll see. But in quantum theory, we like operators, so I'm going to give you operators because you've got a.
Go ahead.
Yes.
I was confused. Like, I can still use the operator tensor description for any operational theory, right?
Okay, there's an interesting question there, and some guys are working on like you've got some objects that span a vector space. So if you've got some general theory, and you can just make these operators span the vector space that you're interested in, then you can probably do that. There was some project that was involving one of you two guys, or both of you two guys, with Rob about. Sorry.
The Hermitianizing.
Yeah, that's right. Yeah. So that if you pursue that project, both of you were doing that. Is that right? Yeah. Yeah. So that would be a project you could pursue. And you should pursue. Like that should be that work should be finished. I mean, the problem, you might get into problems with sort of orthogonal vectors in your Hilbert space will no longer correspond necessarily to preparations that can be perfectly discriminated, things like that. But maybe that doesn't. Yeah, still. But for the moment, I'm interested in getting to quantum theory. Okay.
And you said you're not doing the 5 axioms.
Well, there will be some axioms later. It's not. They're not. This is not an attempt to derive quantum theory from reasonable axioms. It's rather an attempt to restate the standard operational framework we have, but in this kind of setting, and there will be axioms for the time symmetric, the time forward, the time backward. So they're basically mapped very much to the normal axioms we have in a standard textbook on operational quantum theory. Yeah.
Okay.
Sorry, I know we're stopping too much. Just a quick question to see if I understand. Were you from the beginning assuming that the thing you were describing in the lab was quantum theory? What I'm confused is if these things are always equivalent, and all we assumed was essentially tomographic locality and the whole structure that works for any operational.
So, let me show you how it works, and then we can have this discussion. But this picture here is just entirely general.
Right.
But then to do that thing with duotensors, I did need to use decomposition locality, which is the same as tomographic locality. But I wasn't using any other aspects of quantum theory.
Okay.
But now I'm going to start to introduce quantum theory, and you can see how it starts to come through. Yeah. Okay. Okay, so correspondence basically is the idea I just told you. We say we've established correspondence from operations to operators if under this correspondence any circuit comprised of operations has probability equal to the evaluation of the corresponding circuit comprised of corresponding operators. Okay, so just the thing I just told you. And I'm going to assume decomposition locality, and there's also an assumption that certain fiducial matrices can be made to match, and you'll see this in a moment. Okay. Okay, once you've got this correspondence, the relationships you have in the operational theory go through under correspondence and become relationships in the operator tensor theory. Okay, the only difference being that in here you have equivalence, but in the operator tensor theory you just have equality. Okay. Because
I think for me it's not very clear what's the difference between the operator tensor and those things you had with the white dots.
okay, I'll come. This will become clear in just a moment, in a few slides. Yeah. Okay, so here's an operator tensor. I've kind of shown you this already. You define, so you have Hilbert space associated with each system, and you take the tensor product of the Hilbert space and its conjugate, and then you define this space as equal to that tensor product, and then this V is the space of emission operators inside here. Okay. And then for the pointers, you just have n-dimensional real vector spaces. So here's an operator tensor. If you look at the systems and so on going around, then it's an element of this big space here. And you can, in fact, in quantum theory, it will end up being an element just where you have emission spaces. Okay. And there's a story which I tell in the book about how this relates to circuits evaluating to a real number. Okay. If you allow your operator tensors to be non-Hermitian, then you can get complex numbers when you evaluate your circuits. And you want your circuits to evaluate to probabilities. So this is really the reason why you put emissions everywhere. Okay. And then I should explain what this means. So here is a very simple circuit where I have some Hermitian operator, wire going up, and another Hermitian operator. You can represent that symbolically by this, so you have a repeated index. And then what I mean by having this wire, or this repeated index, is that we're taking the trace. Okay, so this circuit here is just equal to the trace of those two operators. But we could also have a situation like this, where we have sorry, I'm doing it the wrong way. Like that. And so now I'm still tracing over this wire, but I've got one wire left open at the end. Okay. So what about an expression like this, where these two boxes become just one thing? Well, just by linearity, what that means is you're taking the partial trace. So what these wires mean in a operator tensor circuit is that you're taking the partial trace over the corresponding part of the Hilbert space. Is that clear? And one of the nice things about this notation is you don't have to keep writing trace all the time, because it's implicit in the wires. Okay, and you can tell a similar story for pointers, but now what you have is a dot product between these vectors, basically. So the same kind of story, but instead we have this this real vector space. So we're just taking the obvious dot product in that case. Okay.
What's the meaning of the sub?
Yeah, good question. The subscripts.
Yeah,
So in the diagrammatic notation, you can look at that picture and see what it means. But in the symbolic notation, so imagine, just to illustrate, imagine I had A here and A here as well. In the symbolic notation, you can't see where your wires are, so you put those indices on to tell you which ones are connected to which ones.
Okay, thanks.
It's one more reason that the diagrammatic notation is much nicer. I think every time you see symbolic notation, it's just because I got lazy and I didn't feel like spending the time to draw the picture. Okay. So here's a circuit, and everywhere there's a wire, you trace, you do the partial trace or the dot product on these pointer wires. So it ends up evaluating to a number. And if you restrict to Hermitian operator tensors, then the number you get will be real. You have to impose a little bit more to make sure they're positive, and a bit more to make sure they're non-negative, they're not greater than 1. But we'll come to that later. Okay. Okay. There's an assumption here which I almost want to skip past and come back to. Well, maybe I'll just say this. There is an assumption which goes into this, which is basically saying that your pure preparations, those are the ones around the rim, correspond to rank 1 projectors. Not necessarily normalized rank 1 projectors. In fact, they won't be in general. And then also vice versa. For every rank 1 projector with an appropriate normalization, there is a pure preparation. So this is already setting up a correspondence between quantum theory and so this goes some way to answering this question about what is it that makes us quantum. So we kind of want to do that for various reasons, so we can construct the theory. Okay. Okay. Now what we're going to do is exactly the same thing we did in the general operational case, but we do it for operators. So we can introduce sets of fiducial operators. Okay. And when I was telling this story before, I wasn't really being honest because these things are mathematical objects, whereas I was telling it about operations. Now I'm being honest. These things, this would be an example of a set of fiducials that you could use to expand a general preparation operator. Oops, sorry. Okay, so you do that here, and it's also with the fiducials. Okay. And then you can form the fiducial matrices. So this is all the same as before, except that these fiducial matrices are equal to the sort of the circuit formed by the fiducial elements, because this is all mathematics now. Okay. Is that clear? Everything's straightforward.
Maybe I missed one little bit. So for the vertical wires, which
Yeah.
are operators on
Yeah.
the spaces, right?
Yeah.
But is the fiducial elements you choose, do they basically just correspond to like matrix elements, or like any orthonormal basis in the Hilbert-Schmidt inner product?
So you could take them to be a spanning set, but you are going to want them to make them correspond to the things you can do in a laboratory. So in quantum theory, you want them to be positive operators. Yeah. Okay. So yeah, you get this same cancelling of black and white dots, the same as before. Okay. Okay. Here's the key thing now. So now we can expand an arbitrary operator tensor, which is Hermitian, as a sum over these fiducial elements. Okay. And that's something that works in we know that kind of thing works in quantum theory. It works for complex, for quantum theory based on complex Hilbert space. It doesn't work if your underlying Hilbert space is real or quaternionic or something like that, but it does work for complex. Okay, any questions?
Just because of the failure of tomographic locality.
Yeah. And here now we have equality, not equivalence, because this is not about the laboratory and sums of things, but it's just straight up equality. Okay. Okay, so now we're going to go through the same sequence of steps, but using operator tensors instead of using operations. So we start off with a calculation like this. Okay. And I can replace each operator, like this one, with the corresponding decomposition local form, like this. There's the B1. And then I can recognize that I've got these fiducial circuits for operators inside, and so I can replace them with just the thing. And this is equal to the previous one. And then I can just cancel over the black and white dots because of my notation and write it down like this. Okay. So we've seen that we have two different ways of getting to this same expression in terms of duotensors. And if the fiducial matrices are the same as in the operation case, then we get the same answer. So that having these fiducial matrices be the same is essential for this to work. Okay, so now we can state the correspondence theorem. Which is this. If the fiducial matrices coming from the fiducial operations are the same as the fiducial matrices coming from the fiducial operations, so operators, so this is true for pointers and this is true for systems, then this operation, which is expanded like this, corresponds to this operator, which is expanded in the same way with the same duotensor living in the middle. And you can see this works because if I start off either with the circuit of operations or the circuit of operators and do the calculation, I get to the same calculation in both cases as long as the fiducial matrices are equal. So that's the thing I've been aiming at. Does that make sense? Is that all clear? No? Okay.
Basically, the correspondence between this operational theory and the operator tensor theory reduces, in a sense, to the correspondence between the fiducial.
Yeah, in a sense, yeah. Given this decomposition locality assumption, otherwise it wouldn't work.
If I didn't choose the same fiducial, then probably I'd just have some sort of like transformation.
Yeah, and I imagine you could explore that. It might even be quite interesting, but I mean, there is. Yeah, I mean, these things, I call them duotensors, and I haven't much explored the tensor properties of them, which would be looking at these transformations, and I think it might be more interesting than you would think, because, and also I call these objects operator tensors, and again, there's going to be some tensor-like properties under transformations. I think it's probably more interesting than you would think, because I think it might take you into representing quantum theory in a way that's not the normal way you'd think of. So that's an avenue.
Usually, so that kind of like gauge independent.
Yeah, that's right. Yeah, that relates to that. Okay. So, and then when you have this correspondence theorem, you can prove a correspondence rule, which is that equivalences and inequalities go through under correspondence. So if you have some equivalence between some expression over here, remember I wrote down expressions in, I forget which lecture that was, the first or second lecture, which can be sums of networks with coefficients in front of them, so weighted sums of networks, real weighted sums of networks. So if you have something like this, then that becomes equivalent to the corresponding expression where you have now operators instead of operations. Okay, and you get something similar here for inequality as well, which I haven't talked about so much. Okay. And then, so using that correspondence, you can take the physicality conditions I wrote down. So for time symmetric theory, you have double causality, so these two conditions, and you also have a positivity expression. And those physicality conditions go over into operator tensor form. One slight change here is, well, one change is that you get equality rather than equivalence. Another thing here is that we've assumed that there's a map, there's correspondence between pure preparations and rank 1 projectors, and the same for pure results. Okay, so now this positivity becomes this condition. Okay, and this gives a lot of quantum theory, actually. This is giving you a lot of structure in quantum theory, because it has to be true for all rank 1. Okay, and then you can have some axioms. Remember, we're in the simple book, so these are some axioms for operational quantum theory. And these are not meant to be sort of pleasing, sort of reasonable axioms. These are sort of still quite mathematical, but they're in this new language. And they're kind of familiar to you. And you have these axioms, well, let me just state them. So all the realizable circuits are directed acyclic graphs. You don't want to have circuits that have wires going back in time. All realizable operations are physical. You want that so that your probabilities are between 0 and 1 and you don't have unphysical causality. Every realizable operation has a physical operator corresponding to it. Okay. And every physical operator has a realizable operation corresponding to it. So there's this one-to-one map between operations and operators.
What physical operator? Or?
Yeah, so physical means it satisfies these conditions.
Okay.
Yeah.
Sorry, yeah. Okay.
Yeah, well, actually, I'll have a bit more to say about that. In the time symmetric case, physicality means it satisfies these conditions. Okay. In the time forward case, you only have this condition, not this one, and you still have a positivity condition, but with no incomes. So, yeah, time symmetric, it's the ones on the previous page. The time forward, you only need to have the forward causality condition and an appropriate positivity condition. And in the time backwards case, you get you want just a backward causality condition. And yeah, go ahead.
In item 2, when you say physical operator, the
Two, yeah. The
operator here, am I right that it's you're talking about the double-walled boxes with an output? So usually when I hear the word operator, I would think by default about operators on a Hilbert space, but these are more like operators between operators in the Hilbert space. So they're more like quantum.
I mean, they live in this space, which is, you remember I had how the operator tensor, maybe I should just go back and answer this. So many slides. Yeah. So they live, an operator, or sometimes I say operator, sometimes I say operator tensor, but I mean the same thing. So these operators live in a space which is dictated by the wires going in and coming out. In a quantum case, I want these things just to be Hermitian, and I define it up here. Now, There is the normal way of thinking about it, you say that operators act on Hilbert space and so on. There's a worry about a sort of time asymmetric way of thinking creeping in, that you're thinking that it does something to the state that comes into it and the state comes out of it. I mean, it's mathematics, but it has this time asymmetric connotation. So I prefer to say it like this, but I think it's an equivalent way of talking.
That so it can be interpreted like each of those V's is a space of operators.
Yeah. This is equivalent to the usual point of view. Like normally you might say,
yeah, it's kind of like in a sense, the Choi representation.
Yeah, I think that's right. Yeah.
Is there a reason that you haven't taken the dual of the V's on the right, so that the out? I would have expected either the output A and C or the input ABA to be dualized, so that there's a distinction between.
Oh right.
Which ones were the inputs, which ones were the outputs?
I mean, you have got superscripts and subscripts. Whoops.
Oh, right.
Which I think is doing the job of that. Yeah. So I don't think you need to.
In quantum theory, these B box, they are like super operator.
Yeah. That would be a super operator. Yeah, and then you wouldn't have the X, the input, so the income, you wouldn't have that, but the outcome would be the label on a set of super operators that you have. If those labels correspond to outcomes. Yeah. And so that set of axioms is equivalent to the usual set of axioms. Just get back to that. Yeah, there we are. The time forward case, at least. Then you have. So forward causality essentially imposes that if you sum over those super operators, you get something which is trace preserving. And test of positivity is the completely positive map constraint. So this is completely familiar as a standard representation of quantum theory in the time forward case. In the time symmetric case, it's a bit different, and it as I showed previously, it's equivalent to standard quantum theory, but
So axiom 0 and 1, they are only on the operational theory part. It's not about the operator tensor representation.
Yeah, I guess that's right. Yeah, because this is in a laboratory, and likewise this one is in a laboratory. Yeah.
And then 2 and 3 connects to the operator tensor.
Yeah, that's right.
And what's special about quantum theory here? What makes it quantum?
Well, I mean, you have this is equivalent to the usual constraints in terms of the constraints you have in standard approaches to quantum theory. So, and one comment is that preparations are like completely positive maps that have nothing coming in the bottom, the trivial. So this gives you the set of constraints on preparations corresponding to density matrices, which are subnormalized,
right?
And so on. So everything is in here.
Right. It's the tester positivity.
Yeah.
Singled out the positive semi-definite operators.
Yeah, that's right. Yeah. Exactly.
Not only the test positivity, but that purity condition applied to the operators, right?
Well, but you get this in here because because the positivity condition under correspondence has rank 1 sandwiching it. Yeah, so that's here. Yeah, exactly. Yeah.
The very definition of the operators already carry this purity.
Yeah. So that purity correspondence is a big. There's a lot being done there. If you relax that, then you could pursue maybe sort of finding other GPTs that map into Hilbert space.
Yeah.
So what's the purity correspondence?
Okay, I'll go back. I don't like it, but I don't like the way I've written it because I've written it using this old notation. but it's this one here saying that
I see. It's
every
okay.
pure preparation is proportional to is equal to some rank 1 projector, and every rank 1 projector with appropriate normalization is equivalent to a pure preparation, and the same thing for results as well.
So this purity correspondence is not one of the axioms, but it's built into the framework of operator tensors.
Yes.
It's built in, and specifically because you have it, you then sneak it in here. Yeah.
Okay.
Yeah. Okay. So I think I've got 15 minutes, and probably 100 slides. What I'll do is I'll just start to introduce this topic of Hilbert objects, and so just to give you again the overview, we started off in the laboratory, we extended it linearly to give us this equivalence framework. We set up correspondence with this operator tensor framework using duotensors down here. And now there's something else to be done where we want to go from Hilbert objects into the operator tensor framework. And we're used to the Krauss, the Krauss way of writing a super operator, let's say. And there's a whole bunch of structure that lives here, and it's all very interesting, and you use that to prove all kinds of theorems in quantum theory. So it's worth delving into. So one example of a theorem is the Steinspring extension. Steinspring dilation, which has a different form in the time symmetric case. Okay, so I think I'll just go a few slides into this and just start to explain how this notation works. It's once you understand what I'm doing, it's all very familiar. Okay, so this is just an overview, and then I'll go into more detail on the next slides. So a Hilbert object, you have left Hilbert objects like this, which is an element of a tensor product of something going in the bottom and something going in the top. I introduced these bobbles, which, remember, I told you that was a knitting term, and is also homage to Bob Kirker. Often in the literature people use arrows, and sometimes they use arrows that point up on the left-hand side and down on the right-hand side. And if you're writing a book on time symmetry, that gets very confusing, because the ones that point down are pointing against the direction of time. But all you really need is some left-right asymmetry. So these bobbles, I think, do the job better for this doubling up. Or sometimes people use thick and thin wires, but it's hard. So you have to look very closely sometimes to see whether it's a thick or a thin wire. So I think my bobbles are far superior to all the other notation out there.
Bubble me in the knitting.
I think, when you knit sometimes and you get those little dense bits of wool that form little, and you make a pattern of them. So that's what it means. So it's an appropriate term. And I must have had this word back somewhere in the recesses of my memory. I can't explain it. Yeah.
Oh, it's very neat.
Yeah. Okay. And you can draw this using the composition package, which is based on. Okay. So then you get this kind of doubled up notation, and that's this one here. And so if you see what that is, this will be familiar to you. This is just the Krauss decomposition. And normally people write it as if the density matrix is coming in the bottom. So you have normally you're familiar with this kind of a density matrix acting on rho. It can be written as a sum over L. Often people use E rho. I got that right, yeah. Something like that. But instead of you can put a dot here and then a dot here to indicate the absence of the thing, and that's what we have here. This is the same thing as that. I call this two-fold form because you can sort of fold it. It's kind of got that fold. And the other reason I call it two-fold form is I was looking for something that began with a T because I already have test of positivity. And two-fold form, if you can write this in two-fold form, it's equivalent to test of positivity. Okay, that's not obvious, but it is essentially a standard result in quantum theory. Like the Krauss form, the Krauss form guarantees positivity. Okay. So this is the whole picture. We have these operations, we have these operator tensors, and now we want to have these this kind of Krauss form.
And the Hilbert objects are just half, they're left, right? Like what are they?
Yeah, they're things. They're basically things you make out of these Hilbert spaces. So you have left Hilbert objects, right Hilbert objects. In the book, I also talk about more general Hilbert objects that might have left and right parts built into them. In fact, an operator tensor, you could also think of that as a Hilbert object because it's kind of symmetrically formed to the left and right. But you can have bits that are asymmetrically formed.
All of them are Hilbert.
They're all Hilbert objects, yeah. Okay, so let's just start with the basic Hilbert objects. So we have here this antiquated notation in terms of bras and kets. So we can define, there's 4 Hilbert spaces, and these are the things that belong to them. And then we have superior notation for the same objects using this diagrammatic notation. Okay, is that clear? Okay, and there's something maybe I can just point to this now, and I'll talk about it again later. See on the left side over here, you've got there's a ket, but this is a bra. And there's a reason you do that, is because you want to be able to take the scalar product. But it makes it really hard if you want to form this thing. Okay, because this thing is a left object, but you can't write a left object that has an input and an output as either a bra or a ket, because it has the output part has got a bra and the input part has got a ket. So that's the real problem with the standard notation. It's kind of got this unfortunate twist in it. So this notation is why it's entirely superior. And this thing I'm showing you here, this is not original to me. You'll see not this exact diagrammatic notation, but this kind of thing is happening in, say, the book of Kircher and Abramsky. It's kind of key to these diagrammatic approaches. Okay, so you can take the scalar product. Diagrammatically, you just join a line with a bubble on it, and that's equivalent to these things. And if you flip this scalar product here to get this one, you're taking the complex conjugate. Okay, that's familiar to everyone. You can take the sum over Hilbert objects. So in antiquated notation, you would write it like this. Here's a sum. In the new notation, you can write the same sum like this. Is that clear?
So can you study?
Yeah.
And these alphas, they are like between 0 and 1, or?
No, they could be any real coefficient. So no, actually any complex coefficients. Yeah, it can be any numbers. Yeah.
So even though these scalars, they don't live in the time-symmetric operational theory, but once we are in operator tensor theory, then we somehow get this.
Well, if you're doing mathematics, you're allowed to just put anything you want in there. If you want to make these things physical, correspond to something, then you have to pay attention to what values they can take. But yeah.
Okay, thanks.
Is that clear? Okay, so I described this one, but you get the same thing for each of these 4. And you can see you can kind of flip between here and here, and between here and here, and you're taking a kind of conjugate, if you like, when you flip, because this becomes, you take the conjugate of these expansion matrices. That's the natural thing to do. We used to in quantum theory. Then you can also take the sum over some tensor product of these things. So here I've got 1, 2, 3 of them, and I'm taking the sum, and you get that object. And now you can see the point I was making. This thing, which is a naturally occurring object in the theory, you can represent it as a left Hilbert object, but you couldn't represent that as a ket or as a bra.
But can't you just put...
Well, okay, you could represent it as a sum over some weirdly formed objects, but here I'm just representing it by one object. Yeah, so it's unnatural to write it in terms of kets and bras. Okay, and then you have the sort of conjugate object on the other side. Okay.
So, is this kind of like an entangled state?
Well, this is not this has got inputs and outputs.
Yeah.
But if you got rid of the input there, then that could be an entangled state for sure. Yeah, if with an appropriate choice of an entangled pure state. Yeah. That would be a way to write it down. Yeah. Yeah.
So if we were to double this up,
Yeah.
then we would get an operation which is pure and it corresponds to a rank 1 projector,
Yeah.
which corresponds to a state in the, or like a vector in the Hilbert space,
Yeah.
which is entangled.
Yeah. Yeah. That's right. Yeah. Yeah. Exactly. Yeah.
If it is entangled or not, does it depend on
The
the coefficient?
Yeah. It would depend on those coefficients. Yeah. Yeah. Okay, you can construct more general objects. So here's just, I guess, some random thing I drew. Here you've got this expansion matrix. I've also put some labels going in. Okay, and I call this a hypermatrix. I guess if it only had a label 2 wires, it would be a matrix, but it's got more than 2, so it's a hypermatrix.
We should not think of like L, B, H, and K as incomes and outcomes, right?
You think of those just mathematical labels. They take values. L can take values from 1 up to whatever.
Right, and then this D thing is also not an operation. It's just a matrix.
This is a matrix, yeah, and you can have complex entries in it.
So it's only when the horizontal wire is connected to the double edge of the boxes, then they are income outcomes.
Yeah, that's right. These ones, when they connect to the double. For the moment, I'm not putting any pointers in, so there's nothing connected here, and I won't do that when I'm talking about Hilbert objects with these flat edges, because it just doesn't play nicely. Yeah. So I want to study these hypermatrices, and so here's a hypermatrix. I've put a black dot in it, and the black dot is so you can follow some transpositions I'm going to do on the next slide. The thing to notice, this has horizontal structure. It's got wires on the left and on the right, and it's got vertical structure because there can be multiple wires going up and down both sides. These things are especially interesting to us when they're used to expand Hilbert objects or operator tensors in terms of bases, but that's something we'll come to later. Okay, here's the transpositions. So there's essentially 2 kinds of transpositions. You can do a horizontal one where you pull the wires that were on the right over to the left, but you keep their vertical order. Okay, And you can do a vertical transposition where you reverse the order of the wires vertically. If there had been 3 wires, then I guess the middle wire would have stayed in the same place, but you reverse the others. But you don't mess with the left and right. And then you can also do both. You can both do the vertical and the horizontal transpose, and that just leads to the transpose. Okay, and then there's some group theory on these things, which is kind of obvious. If you do the horizontal transpose twice, you get back to the thing you started with, and the same is true for all those transposes. Then the transpose T is just equal to applying V then H, or H then V, and so on. You can just write down these relationships. These are the properties of the Klein-4 group. I had to search the internet to find out that. They're the symmetry. It's the symmetry group of the non-square rectangle. Okay, and then, well, I'll just do. Oops, I'll just finish this and then solve that. You can also define additional things where you also take the complex conjugate of each of the entries. So here are the 4 things I just showed you. This one is the starting object, and then these are the horizontal transpose, the vertical transpose. No, sorry, that's right. Horizontal transpose, vertical transpose, and just the transpose. And then you can do all those same things, but where you now also take the complex conjugate of the entries. Okay, and these play a big role in quantum theory. Is that clear?
So usually, for the sake of flipping the diagram like this as a conjugate rather than as a transpose, and I thought that was what you were
so for these hypermatrices, that's right. For the hypermatrices, as I'm talking about, you want to put, you have to be a bit careful whether it's contraposed or not. So I represent that by the overline. When it comes to the Hilbert objects, flipping it will also perform the conjugate. Okay. These are sort of expansion matrices. So just going back to here. Oops. Here's an example. There's a hypermatrix. When I flipped it, I also put a bar over the top. So it's the same thing. And then all of these things, I give them names. So doing nothing is identity, horizontal transpose, vertical transpose, transpose. And then just putting a complex number on top of them, that's the conjugate. If you do the conjugate and also the horizontal transpose, you get the horizontal adjoint. It's the vertical adjoint, and then just the adjoint. Okay. And I should probably stop there. These things all play an important role in setting up this sort of general theory of Hilbert objects that's important in quantum theory. Okay, I'll stop there.